all and welcome to this lecture. We are in module 10, lecture number 4. In this lecture, we are going to introduce the quasi-static operation of MOSFET, meaning till now we have discussed that our MOSFET is only governed by DC voltages. We have applied DC voltages as VDS, let us say Vs is grounded and we connected a gate voltage VGS. So, these are the DC voltages. However, we will see what will happen if you vary these terminal voltages slowly. That is what quasi-static operation is. We will see how the terminal currents in quasi-static operation is related with the terminal voltages. These are the learning outcome of this lecture, which help you to understand the basic underlying physics of quasi-static operation in MOS transistor. It will help you to relate the terminal voltages with the charges and the terminal currents. We will formulate the terminal current expression in quasi-static operation using charge voltage relationship and Kirchhoff's current law. So, let us do a quick recap. In previous lecture, we were discussing about the classical and modern scaling techniques. We said that the growth of the semiconductor industry is dependent on the scaling, meaning how efficient you scale the long dimensions of the MOSFET to a short scale, right. We said that classical scaling follows some set of rules, out of which we divided into two parts. One is constant voltage scaling and one is constant field scaling. However, when we are approaching towards the new emerging devices, then these set of rules will not fit everywhere, and hence we need to use some scaling parameters as per case by case. That is what we said, that quasi constant scaling, meaning we will decide a scaling parameter k dash which is not exactly k or not exactly 1. So, somewhere it lies between k to 1. We also discussed about the emergence of semiconductor devices in terms of FinFETs and gate-all-around structure, which increase the gate electrostatic in the channel. Now, let us get started about the quasi-static operation. Till now, we have only discussed about the DC voltages which we are applying in our MOSFET, right. However, what will happen when you put these devices in the circuits? When these devices will be used in circuits, the terminal voltages will vary. So, in this module, we will discuss about what will happen if the terminal voltage will vary very slowly. That is what is called quasi-static. The analysis will evaluate the charges and the terminal currents during large signal dynamic operation, focusing primarily on the intrinsic part of the devices. Here, intrinsic part of the devices means it is related to inversion charge, bulk charge, gate charge and oxide charge, as well as some amount of substrate electrostatic. At this stage, we are ignoring the extrinsic part of the MOSFET, which, yes, obviously it will control the overall MOSFET operation. So, we will see the influence of this external effects in later modules. Now, to do this analysis, we are going with some simplifying assumptions. One is, at this stage we are considering the channel length and widths are long, meaning there is no short channel effects. The substrate is uniform, and as I mentioned that we will ignore the parasitic resistances, meaning the resistances or capacitances from the external part of these dotted area. We will also assume the low speed regarding operation frequency, meaning the magnetic field is disregarded. We will only assume that the basic electrostatic law holds good and the MOSFET still under quasi-static operation follows the Kirchhoff's law, right. So, we will follow or we will use Kirchhoff's current law and Kirchhoff's voltage law to formulate the quasi-static operation. So, let us see first our fictitious MOSFET. In this structure, we remove the source and the drain, and considering there is a source and drain which is related with this channel. So, to understand this, we are not connecting the voltage with respect to body or source, we are just showing the terminal voltages separately. Here this terminal is gate, this terminal is source, this terminal is drain, and this terminal is body. In each terminal, the DC voltages has been applied, which is nothing but Vg, Vd, Vs and Vb, and these voltages are measured with some common reference which is termed as ground here. We do have relative current in the terminals. You can see all the direction of the currents is considered inward in the device. Next, we do have charges available in the intrinsic part. These charges are nothing but inversion charge, bulk charge, gate charge and oxide charge, correct. Similarly, we can use the common notation which we have followed in our previous fundamental analysis, that the channel length varies from 0 to L, and this is the x direction, this is the y direction. With these assumptions, we are moving forward to relate these terminal voltages in quasi-static operation. But first let us see what we have done so far in DC analysis. In DC analysis, we said that when you apply the drain voltage, the charge or the electron will come from source and ultimately it will go to drain, which give rise to a drain current, right. This current in the channel is denoted by transport current. So, IT stands for transport, and under DC operation we said that this transport current is nothing but drain current, which is exactly equal to the source current. So, IT can be written as minus of IS, whereas here IS is considered inward into the device. Additionally, you remember we started our DC analysis when we were talking about 4 terminal MOS structure. We said that the gate current is 0 and the body current is 0. The same assumption we are taking here also, which means the insulator is purely ideal and hence there is no gate current through it. That is what I mentioned, we are not considering the short channel effect, and we are also considering this bulk charge is good insulator and hence there is no current which is body current. So, we have already done this kind of analysis. In general, we showed the terminal voltage with terminal current as with some function ht, where ht is some random function of transport and the current is ultimately related with the terminal voltages as Vd, Vs, Vb and Vg in closed form. For example, if I write the drain current equation for either saturation or non-saturation, let me write for non-saturation, it is W into mu into Cox dash divided by L into Vgs minus Vt into Vds minus alpha times Vds square divided by 2. Here you can see the current is ultimately related with the terminal voltages, where Vgs is nothing but what? Vg minus Vs. So, we do have terminals Vgs and Vg and Vs, which is this and this. Similarly, Vds stands for Vd minus Vs. So, again the current is function of terminal voltages like Vd and Vs. We do have a function Vt where explicitly Vsb is coming. Again this current becomes a function of Vs minus Vb, or it becomes the function of all the terminal voltages. That is what the reason to write a simple form of current in terms of all terminal voltages. Now, we have also discussed about the charges. We do have inversion charge, bulk charge and gate charge. Along the length, these charges can be explained as Qi is equals to W into 0 to L Qi dash dx. What it means is, in our previous analysis we have discussed that Qi dash is the charge per unit area. So, if I want to calculate the total charge available in the channel, then I need to multiply with the area. However, this charge varies with x. So, what we are doing? We are multiplying with W, and 0 to L dx will give you the total length with which my charges are varying. In turn, I can simply write these equations as Qi is equals to W into 0 to L Qi dx, where dx or x is this direction. Qg can be written as W into 0 to L Qg dash dx, where again Qg dash is what? Charge per unit area. And Qb can be written as W into 0 to L Qb dash dx. These are the equation what we have already derived for DC operation. Now, let us see how we can relate these charges in terms of terminal voltages. Here we have shown the terminal current with respect to terminal voltages. Now, by using the same concepts, we can use or we can represent the terminal charges or the charges inside the intrinsic region in terms of terminal voltages. Here this is some function which is Fi. Again here the charge becomes a function of Vd, Vs, Vb and Vg. The purpose of this will be clear soon when we will discuss about quasi-static operation. So, this is what we are doing is just to represent, this is what we are doing is just to show how we can represent our previous analysis in some closed forms, right. So, we have already shown that how we can show the terminal current as a function of terminal voltages and how we can relate the charges with respect to terminal voltages, right. Here in DC operation we have discussed that the bulk charge is coming when you applied the gate voltage, meaning at that instant we can consider the bulk charge and the gate charge is the stored charge in the system, meaning when you applied the DC voltage in the steady state, because it is DC, in the steady state Qg is applied in the gate. In response to Qg, Qb will come, and this is can be considered as stored charge in the device. However, Qi is not a stored charge. Inversion charge is the moving charge between source and drain. When you applied Vg, inversion happened. When you apply Vds or the potential difference between source and drain either by Vds or Vdb minus Vsb, then you are actually causing a potential difference such that the carrier will move from source to drain. So, in general the carriers are moving, they are not fixed. So, you cannot consider Qi as a stored charge, but under DC condition when you take a snapshot and see, you will see that Qi considered to be as fixed, but in general Qi is not a fixed charge. So, we need to consider the Qi as a moving charge, meaning what happens is when you apply the voltage, the one electron will come from source and it will go to drain. At the same time, because of the potential difference, the another electron will come and replace the first electron. So, this is completely a statistical phenomena. You cannot differentiate which electron is coming first, which electron is coming later and how they are replacing each other. But in general we can say the Qi is moving charge, it is not a stored charge. Now, let us see how we can relate all these analysis what we have done so far for DC analysis in terms of AC analysis or a slowly moving terminal voltages. As I mentioned that when you incorporate these devices in the circuits, the terminal voltage will vary. So, in this quasi-static operation we will assume that the variation of these voltages, the terminal voltage is very, very small. So, here small v is showing the varying voltages with a capital subscript, right. Like here we have used capital B to show the DC. So, to show the time varying function we are showing a small v and with a capital subscript. This voltage is a function of time. Similarly, this voltage is a function of time. Now, the terminal voltages is varying. Now, what about charge? Obviously, when you are changing the voltage from the terminal, the charge inside the structure will vary. However, when you consider the quasi-static operation, meaning the variation of these voltages is very, very small, So, it is closely equal to DC analysis. That is what charge voltage relationship that is what the charge voltage relationship remain valid under quasi-static operation. In the sense, let us say you have applied a very small voltage and take a snapshot. When you take a snapshot, you freeze that particular picture, and when you compare with the DC analysis, it seems exactly identical. That is what the quasi-static operation means. However, make sure the current, it is not follow the same analysis what we have done so far for DC. Why? Because when you change the Vg, let us take an example. Why? Because to understand this, let us say take an example. You are changing the gate voltage very slowly. When you change the gate voltage, in response to change in gate voltage, the gate charge will change, and hence there will be a current which is Ig. This is nothing but dQg divided by dt, where Qg is the charge in the gate which was the result of change in the gate voltage. However, in DC condition we said that Ig is completely 0, and that Ig was due to tunneling or some other short channel effect, because you are not changing the gate voltage and hence there is no change in gate charge. Whereas here the current is come up because you are changing the terminal voltage. If you change the terminal voltage, the charges will change and hence it reflects into the current. That is what the terminal current cannot be evaluated under DC current expressions. A time varying gate charge results in a non-zero gate current. That is the example we have taken here to start our quasi-static operation. Now, let us take an analogy to understand again what we are talking about quasi-static analysis. We have taken this analogy when we were discussing about the MOSFET. We are taking the same analogy as we do have source tank, meaning this is a water tank and this is the reference level of water, right. This is a drain tank, again there is a flow of water we are observing, and this is a piston. Increasing VGS means lowering the piston. For example, I slowly open the piston, in the sense what will happen at the same instant when I open this, the water flow from the source will be increases. This is the increase in the water at the channel region will be very, very small, but at the same instant the leaving of the electron will be different and the entering of the water will be different. So, if you take a very small fraction of time, you will observe the channel charge or the water in the channel is increased. That is what it is a quasi-static analysis, meaning the entering of the water and the leaving of the water will be different. That is what in quasi-static operation you cannot say the current which is flowing from drain to source, that is IDS, is exactly equal to ISD, right, with a negative sign. You cannot say in quasi-static. However, in DC we assume that this picture attains the steady state, and whatever be the picture we are seeing that the current entering or the water entering here is the same amount of water leaving at the same instant. However, if you consider a small variation, then it will take some time, right. That is what it is not equal in quasi-static operation. We will analyze these analogy of water in terms of charges and the applied voltage. To see further, what we are saying that when you change the terminal voltages with very small speed or slowly you are changing the terminal voltages, it will give rise to a change in the charge. As I explained, if you change the gate voltage, let us say very slowly, then this change in gate voltage will create a change in gate charge, and the gate charge change with respect to time will give you what? The gate current. Similarly, let us take an example, either you are changing Vg or you are changing Vb. By changing Vb or Vg, the depletion charge changes. Let us say the depletion charge increased by a very small amount delta into QB, right, because in the initial freeze out condition or in the DC condition, the charge neutrality holds good, in the sense the charge was balanced and the system was stable. So, you were having the electrons here, right, which was maintaining the charge balance, but the moment you vary the voltage very slow, then what happens, the depletion region increases. If the depletion region increases, to maintain the charge balance again, these electrons will push towards the substrate. If the electron will go downward, there will be a current which is upward, and that current will give you what, IB. That is what this IB current, small I B current, is not due to the current which is coming from junction leakage or whatever the current we have discussed in short channel. This current is responsible for the change in the charge, right. That is a new thing we are observing in quasi-static operation. Similarly, you understand what will happen if you change the drain voltage. If you change the drain voltage by a small amount, right, then there will be a change in the current at this side. Or you can take an example as change the gate voltage very slow, right. So, in the same picture, we are changing the gate voltage very slowly. Let us consider, if you increase the gate voltage, what will happen? The inversion charge in the surface will increase. So, if you are slowly increasing the gate voltage, at that instant the inversion charge should increase. If the inversion charge will increase, go back to your water analogy, you are increasing the gate voltage, the inversion charge increasing, or it should increase, then the question is from where these extra electrons are coming up to increase this delta Qi per unit time. We are talking about a very small fraction of time, right, that is what it is, quasi-static. So, in that condition you can assume or you can picturize like some extra electrons are coming from the source, correct, meaning if you increase the gate voltage from Vg to, let us say, Vg plus delta Vg, where delta Vg is very small, right, in that condition the inversion charge will increase by a very small fraction. Then the question is how these electrons are coming or from where these extra electrons are coming. The extra word here is it is not coming up in DC, right. So, we are doing a quasi-static, means the extra electrons are coming from outside to provide this or to maintain this increase in inversion charge. In support that, if you see, this is an extra flow of electron coming at the source side, and hence there will be an current in this direction, which is what, ISA. So, here A is an additional word, right. So, we are defining that when gate voltage is increases, then the gate charge or inversion charge should increase, the inversion charge should increase. In support, the current will follow this dotted path. However, if you see a picture at the source side, the current is IT is this, right, in response to this IS flowing in this side, or you can take minus IS is equals to IT, or IS is equals to minus IT. That is was the picture we have discussed, but now when the gate voltage is increasing, you have to have some extra electron, meaning the some extra current will flow from channel to source, and that is what we can write ISA. So, if you see closely, ISA, which is minus ISA, is higher than the total current. Similarly, when the voltage will reduce, the inversion charge should reduce, meaning the exit, at the exit end the charge will go little higher, and at the entry the charge will be little lower. That is what the current at the drain side will be higher than the total current, and in response to this the current at the source side will be lower. So, we are defining a new additional current component which is IDA. It is an additional current at the drain side, and ISA, it is an additional current at the source side. This additional current is actually in due to change of Vg very small, right. Now, if there is a current we are defining, definitely we need to define some fictitious charges. That is what I mentioned, from where these charges are coming. They are coming from some extra sources. So, in response to this, we will define the extra charge at the source as Qs and extra charge at the drain as Qd. Now, we will see how we can relate this charge and current with the total current. So, if you write the equation for total current, that is IT is equals to ID plus IS. So, now you can write the total current IDT plus IST is nothing but the rate of change of inversion charge per unit time. Meaning, if you applied a gate voltage very slowly, the inversion charge changes slowly, right, and that is in response to giving you drain current and source current. Whereas, if you consider the DC condition, what will happen to this quantity? The rate of change of inversion charge per unit time we consider to be 0. We are not considering that inversion charges are changing with time. That is what we can simply write ID is equals to minus of IS. This holds good under DC condition. However, when you are talking about quasi-static or time varying signals, then IDT plus IST should hold good, and it will give you the rate of change of inversion charge, right. Now, we can define IDT again as the total current plus some additional current. Just now I explained, this additional current is in response to leaving or removing the extra charge from the channel. Similarly, IST can be written as the total current, which is just reverse the source current, plus ISAT. Here ISAT is positive because you are having some extra electrons coming in the source to maintain the charge neutrality, and hence this current direction is from channel to source. That is what we are taking positive. Following this equation, we can rewrite this equation as IDAT plus ISAT is equals to dQi divided by dt. That is given here. Meaning what? The extra current which is coming at the drain and source will give you nothing but the rate of change of inversion charge. These currents are called charging current. Clearly speaking, at this stage, that you cannot clearly identify that which electron is responsible for charging current and which electron is from the mainstream of the current which is coming from drain to source. This is completely a statistical analysis. So, you cannot precisely identify which electron is responsible for this IDA. However, it is clear that if there is an extra current at the junction, at the source side or at the drain side, then there will be definitely charge associated with this. So, let us define some fictitious charge, which is assumed charge, that these charges are coming from extra terminals, right, or from outside the devices. So, in association we can define IDAT is nothing but change in this fictitious charge at the drain side per unit time. Similarly, you can define Qs as a fictitious charge which is coming from the outside world to the source, through the source to the channel, right, and this will give you rise to extra current, that is ISA. Now, we do have multiple options to define these charges. Only consideration is that it should maintain the continuity of these derivatives. A simple approach is you can simply rewrite these equations, following these equations and the previous equation, you can simply rewrite as dQd divided by dt plus dQs divided by dt is equals to dQi divided by dt. In a very first order analysis, you can also say that the rate of change of inversion charge is nothing but the rate of change of charge, the fictitious charge which is assumed at the drain, and the rate of change of fictitious charge which is assumed at the source is equals to the sum of these charges will give you the total rate of change of inversion charge. However, this equation is not accurate. for two reasons. The first is, in this condition, to write this equation, we are assuming that Qi is a stored charge or a fixed charge. When you are assuming the Qi as a fixed charge, then only you can rewrite this equation. And the first assumption we started our quasi-static analysis is the Qi is not a fixed charge. So, this is written for very small variation voltages, that is a pure quasi-static analysis. If the voltage varies rapidly, then this equation will not hold and assumption is not valid. The second point why this assumption is not too correct is, you said that we have discussed that you cannot easily identify which charge is responsible for charging and which charge belongs to from the mainstream. However, writing this equation meaning you are specifically or uniquely assigned that this charge is my fictitious charge, right. Here you are saying that this particular charge or group of charge is my fictitious charge, which you cannot do that in quasi-static operation, right. So, because of these two charges, right, because of these two reasons, this equation is not accurate. However, for a first hand calculation and understanding the quasi-static phenomena, we can consider this equation to hold good at some extent. Following this, we can simply rewrite as q dt plus qst is equals to qit. Again, you can simply understand this equation as the charge extra which is coming from the outside plus the charge extra which is leaving from the from the drain end will ultimately give you the rate of change of charge in the channel. Now, if I want to assign or I want to calculate the total charge because of this fictitious charge assumption, then we can assign some weight, because in the channel which started from 0 and ended up at L, these fictitious charges are present either near the source or near the drain. Yes, under steady state analysis they will adjust itself throughout the channel, whereas if I want to define Qs, which is the fictitious charge near the source, I need to assign some weight in terms of the distance x. So, easy hands-on calculation, we can assign a weight as 1 minus x by L in the charge which is near to source. So, it is nothing but W into 0 to L 1 minus x into Qix dx. We have just derived that total inversion charge can be given as W into 0 to L into Qix dx. This is the total charge calculated by using inversion charge per unit area. So, we have just multiplied with the area as W into 0 to L integration dx along the x direction. But now, as we are interested in calculating the fictitious charges, we are assigning some weight. So, this weight will give you a good result or good assumption that this charge is associated near the source. Similarly, near the drain we are assigning a weight as x by L. So, the overall equation will be Qd is equals to integration 0 to L into W into x by L Qi dash dx. That is what written here. Now, to understand the quasi-static phenomena, we need to relate these change in charge, change in current with respect to terminal voltages. So, we can simply relate by rewriting the equation in terms of DC. As I mentioned, the quasi-static operation is close to DC if the variation of the voltages is very small. So, we can rewrite this term again back to the DC, right. It means with a capital Q and with a capital voltages, and then we can relate with our well known equations what we have derived for strong inversion, weak inversion, all reason model and all, and then again we go back and convert these equation in small q's, which will show the variation with respect to terminal voltages, right. So, if you closely observe our analysis of this section, you can find that we tried to relate the charges with the terminal voltages, right, whether it is Vg, Vd, Vb or Vs. Similarly, the charges are whether it is Qi, Qb, Qg or Q naught at the oxide. So, these charges we are trying to relate with the terminal voltages, right. We are interested in the terminal currents. So, if you see closely, the terminal currents can be given as the rate of change of charge per unit time. We know from our previous analysis also, when we created multiple equations which relates the charge and the voltage. So, by some means, if we can use chain rule and we can define as I is nothing but delta Q by delta V into delta V by delta T, then we can find out the expression for terminal currents, where this part we have already done in our previous analysis. In next module, in next lecture also we will see how we can form a relation between charge and voltage in quasi-static operation. This is nothing but the voltage change with time, that we also know, right. The time variable or the change in the voltage with respect to time is given to us. Accordingly, we need to calculate the terminal current. Here make sure that every current component is dependent on the small change in the terminal voltages. For example, if we talk about the body current, so the body charge is influenced by drain voltage, gate voltage, body voltage and source voltage. In some sense, in some consideration, if you assume, let us say the source voltage is fixed, let us say the body voltage is fixed and drain voltage is fixed, and you only want to see what is the body current with respect to gate voltage. So, you can simply rewrite this equation as IBT is equals to delta rate of change of body charge with respect to gate voltage and how the gate voltage varies with respect to time. The similar expression or similar analysis you can do for every current. Here again, this IDA is the extra current due to fictitious charge QD and ISA is the extra current at the source side due to fictitious charge QS, right. So, let me summarize. We discussed about dynamic MOS operation, which involves the time varying terminal voltages. In result with, they will give the change in the charge, right, which is a function of time. Now, we need to relate this change in charge, whether it is an inversion charge, bulk charge, gate charge or so, and then we are interested in to find out the terminal currents. We said that to find the terminal currents, we need to use the chain rule, that is delta Qg divided by delta Vg into delta Vg divided by delta T plus delta Qg divided by delta Vs into delta Vs divided by delta T plus so on. So, here the current is dependent on all the terminal voltages, which is varying very slowly. So, quasi-static operation assumes that the charge voltage relation remain valid when the voltage varies very slowly. However, the current voltage relationship or the current is not valid as compared to the DC analysis. We have taken an example also about the gate current. Ig is nothing but what? Delta Vg divided by delta D. When we were discussing about the DC analysis, we said that the gate current is due to tunneling or short channel effects, whereas in quasi-static analysis, Ig is nothing but the rate of change of gate voltage, right, that causes the gate current. So, we will stop here for today. Until then, take care.